I solve every problem in a series of phases. This is count ways to group overlapping ranges. Okay, this is problem 2580, a medium. Was released in the competition last week. And let's go ahead and get right into it. So you're given a 2D integer array ranges where ranges of I equals start of I, end of I. Okay, so this kind of terminology already is very similar to, task problems, right? Where you have a series of tasks and the tasks have a start time and an end time, or a problem relating to meetings, right? You have a bunch of meetings that occur at different times. When do they overlap? When do they not overlap? Different schedules, right? You have these different ranges for schedules, right? The start time of the schedule, the end time of the schedule. So, always when you approach these problems, try to think about other problems that it's related to. And that is a whole class of problems where it has this exact form, right? There's only a finite number of forms, so try to recognize the form of your problem, and usually that'll indicate the solution, or at least some component of the solution. Not always the case, but in general, it's a good consideration. Anyways, denotes all the integers between start and I and end of I are contained in the ith range. So it's just saying, all these times are occupied by some integer, right? If start I to end I, all those times are occupied by some integer. You are to split ranges into two possibly empty groups such that each range belongs to exactly one group, and any two overlapping ranges must belong to the same group. Okay, so that's a bit confusing, the language there, but the idea is that you're going to have two groups, right? Like how are we going to do this? So we had like group A and group B. Okay? And then you're going to place a range, I guess, into group A or into group B. So, if you have a range like 2 to 5, you're going to say, okay, this can go... If you have a range like 2 to 5, you can put it into group A or you can put it into group B, right? If you had range 2 to 5, and I'll put it in the actual format of which it would be given in the problem. So like 2 to 5 or 6 to 8, right? You could put 2 to 5 over here, and you could put 6 to 8 in here, or you could put them both together in here, right? You have multiple options, and there's a closed form solution. There's a statistical formula to determine exactly how many ways you could do that. But, you get the general sense of what's going on, right? So you're going to put the range inside of a group. So I'm using this idea of the ranges as being like balls, and then the groups are boxes, and you put the balls into the boxes, right? But you can't put a ball in both boxes simultaneously, right? It's not quantum physics or something. So such that each range belongs to exactly one group, and then any two overlapping ranges must belong to the same group. So this second constraint makes it a little bit weirder, right? Because if you had 2 and 5, and then the next range you had was 3 to 6, you'll notice that these ranges overlap because they occupy the same slot. If you thought about it as time, right? If I had a meeting from 2 to 5 and you had a meeting from 3 to 6, we're not going to be able to meet at 4, right? Because we're both busy at 4. So there's an overlap, right? So these things overlap like here, kind of 2, 3, 4, 5, 6. So there's a 3 and a 4 they share together, and a 5, I guess. I'm an idiot. 3, 4, and 5, they share together, so they're overlapping, right? That's the idea of them being overlapping. They cover the same space. So since they overlap, they have to be together, right? So these things are then, since they're overlapped, they're kind of bundled together, right? So this is a bundle now. And since it's a bundle, they're together, so they can only be put into one box or the other box. We can't split them anymore, right? They're now bundled together. So that's the thing about this problem. We put the ranges into groups, but what we really need to do is take all the ranges, bundle them together, depending on if they have overlap, right? If they have overlap, we have to bundle them together, and then we can place them within the corresponding groups, okay? Two ranges are said to be overlapping if there exists at least one integer that is present in both ranges, right? So from 2 to 5 and 3 to 6, integers 3, 4, and 5 are in 3 to 6, and 3, 4, and 5 are in 2 to 5. So there's an overlap, right? This is an overlap of 3, but of course there could be an overlap of 1, whatever. Okay. So we're going to return the total number of ways to split ranges into two groups. Since the answer may be very large, return it modulo 10 to the 9 plus 7. Now, I'm going to tell myself to remember to return it modulo 10 to the 9 plus 7, but it's very likely that I'm going to forget in about like 5 seconds, okay? So just fast forward to the end and watch me forget to do that. Okay, so let's first just do an example, and then we'll think through how we can solve this inefficiently and efficiently. This first example is a little too simple. So let's look at this example. Now, a common way of, describing these objects is, the example is given as we got the input of ranges equaling 1, 3, 10, 20, 2, 5, 10, 20, 2, 5, and 4, 8. Okay, so this is how the input's given. Now, it might be effective to kind of model it model it in a manner so that it's easier to digest. And this is the common approach in which you model these kind of range problems to try to discover something about the nature of the problem so that you can solve it. Now, in order to do that, what we'll do is we'll create kind of like a graph scale, and we'll notate each of the ranges, right? So we'll create this graph scale. And what I mean by that is we're going to note all the ranges. So let me just try to get through this quickly. Okay, so we have 1, 2, 3. Now I have to go all the way to 20, right? Because I'm going to capture all of these slots or all of these ranges. I feel like I'm being watched by you guys. All right, 17, 18, 19, 20, and 21 for good measure, okay? So I'm gonna graph each of these ranges. So from 1 to 3 is occupied, okay? So 1 to 3, 10 to 20, okay, 10 all the way to 20, 2 to 5, okay, 2 to 5, and 4 to 8, okay, 4 to 8. So if you've taken an algorithms class in college, this is probably something you're familiar with, or if you've done other range problems, this is also something you're probably familiar with. And so we have all these ranges, and we want to place them within these groups, right? But the first thing that we need to address is the bundles, right? Because if they're overlapping, they must belong to the same group. So you'll notice here, right, that these two overlap here at these points. So they're a part of the same bundle. And these two overlap here. They overlap here. So they also have to be part of the same bundle. So even though these 1 to 3 and 4 to 8 don't overlap, they share a component of which they both overlap. So technically they all have to be a part of the same bundle, right? So this would be one bundle here, right? One bundle that will apply. And then the next thing would be this last one here, right? It doesn't share anything with anybody else. He's just a loner like myself. And he will be his own element, his own bundle here. So now we have two bundles that we can put in group A and group B. So how many ways can we do that? Well, we could exhaust all possible ways, but they can independently go in either group. So if I have two bundles, I guess the general formula, I'm trying to think about how I'm going to do this, right? I have my first bundle and my second bundle. My first bundle can go in group A or group B. So my first bundle can go in A or B, and my second bundle can go in A or B. So there's two ways to do the first thing, two ways to do the second thing. That equals 2 squared equals 4. Right, so that's a general formula for this, right? Because for this bundle, I can put in either group independent of anything else, mutually independent with all the other bundles. In this bundle, I can put in any group, and again, since the other one was independent of it, then it's mutually independent of that, so it's mutually independent of everything else. So I can put the first thing in 2 spots, I can put the second thing in 2 spots for a total of 4 different ways of doing it. Okay, so I think you get the general idea of this problem. What we want to do is first thing we need to do is find all bundles. And I'm saying bundles basically meaning all the ranges that are overlapped together or share some overlap with some other component like this, right? All the overlaps are together. So find all bundles where, and then since we're finding mutual bundles, then the bundles don't overlap with each other, right? Because if the bundles overlap with each other, then they themselves would make one larger bundle, right? If I said that this one, this, to, change this problem before, if this was like that, this was like this, and that was like this. If I shifted over this bundle, well, then they're no longer separate bundles, right? Because they overlap, so make one larger bundle. So from that, you can kind of deduce that bundles don't share any overlap. So we find all bundles that share no overlap. And then we determine total number of what? Total number of placements, I guess. It's been a while since I've taken discrete math, so some of the terminology is lost within the depths of my mind. So how are we going to do this efficiently? Inefficiently, you could look at an element and then look at all the other elements to see if they... I don't even know how you would do this inefficiently. You could look at an element and then you could look at all the other elements to see if they overlap, and then say that they overlap and they have to be together. Right? So you could build the elements one by one. So you could look at you could look at one element and find the elements of which it overlaps with and call that a bundle. Then look at the next element, find the elements it overlaps with. If it's overlaps with an already existing overlap, you just attach it to that overlap. If not, you put it in its new overlap with new overlaps. If it doesn't overlap, then it's its own bundle. So you have to look at all elements, and then for all elements, you have to look at all other elements. So that would take n squared time, right? And it would also be kind of convoluted because you'd have to think about the intricacies of if something is overlap with something that's already overlap with something else, then it goes in an old bundle. If not, it goes in a new bundle. Something of that manner. And if this is abstract and doesn't make a lot of sense, it doesn't matter because I'm just expressing that I could think of an inefficient solution, right? So here n squared isn't going to work, right? Because if I have 10 to the 5 bundles, for each bundle I'm going to have to look at 10 to the 5 things, and there's 10 to the 5 things, so that's 10 to the 5 times 10 to the 5 is 10 to the 10. It's going to be a time limit exceeded. So that solution isn't going to work. But instead what we can do, like what we do with almost all of these class of problems where we have ranges, is it's essentially sorting, right? We're going to be using sorting. We almost always use sorting when we're dealing with this kind of problem. And the way that we'll do it is think about bundles in terms of where they start and where they end. Okay? So what if instead what we could do is just look at things in order of start time? Okay? So if we looked at things in order of start time, we would look at this one first, and then this one, and then this one, and then this one. Right? So the first thing I'll do is I'll add 1 to 3. And I'll say, okay, 1 to 3, you're your own bundle. Like so. And then I'll add 2 to 5. But since 2 to 5 starts after 1, so it starts after 1, but it ends before 3, that must mean that it's part of the same bundle. So I can remove this thing and say, okay, I've just changed the boundaries of my bundle. The idea is I've added a new element, so now there's new boundaries of my bundle. And since I'm looking at them in order, I'm saying, okay, whatever I processed already came before me. So it came before me. But I start before the previous thing ends, right? So whatever I've processed before comes before me. And if it ends, if if it ends after I start, then it must have some sort of collision. And that's the general idea you just have to get through your head when you're doing these kind of problems, right? Is to understand, like, what are the implications if you look at things in terms of their start time, right? So when I'm adding this element, again, just to make this point as clear as I can possibly make it, because it is a bit confusing, when I'm adding 2 to 5, I know that anything that starts before 2, I've already processed, right? Or anything that starts before or during 2, I guess, because I guess 2 things can start at the same time, right, has already been processed. So when I add 2, I'll say, well, the previous boundary ends after I start. So that must mean the previous thing, since the previous thing ends after I start and the previous thing starts before I start, I'm within the boundary, right? Since I process things in order of the start time. This is so confusing to explain, right? The previous thing starts before I start, right? The previous thing starts before I start, and the previous thing ends after I start, so I must be in between them. So I'm like, okay, Johnny, you started your meeting before me, right? And your meeting's not going to be over until after me, so I must collide with you during your meeting. And since the previous thing starts before I start, right, we're going to be, and ends after I start, we're going to be overlapping. And since we're overlapping, we have to be a part of the same bundle. So now the bundle goes here. The next thing I'll process is 4 to 8, and it's the same situation here, right? The previous thing starts before I start, and it ends after I start, so there's a collision. And since there's a collision, we extend the bundle to here. And then finally, just to get something that doesn't affect it, we look at 10, and we say, okay, the previous thing ends before I start. So the previous thing starts before I start, because that's the order in which we processed it, so we know that's true. But also if I just look, I say, okay, it ends before I start, so therefore there's no collision. And since there's no collision, I'm not going to extend the bundle. Instead, I'm going to create a new bundle, starting from here to here. And then from that, I know that I have one bundle here and a second bundle here. Is there a better way of explaining this? I guess the idea is I'm processing things in the order of which they start. And since I'm processing things in the order of which they start, if I start before the previous thing ends, we overlap, right? And I just have to look at the previous thing to determine if I'm a part of its bundle, right? Here, right? Since this thing starts before the previous thing ends, we know they're a part of the same bundle. But even though it doesn't actually overlap with the initial thing, but we can just establish that it's an ongoing bundle, okay? So basically what I do, I guess for step 1, is I say, well, I'm going to sort the ranges. That's the first thing I'm going to do. And then I'm going to say, does this new range so I'm going to look at each range. So I'm going to look at each range start to end. Right? Start to end. I'm going to say if this new range starts before the bundle I'm looking at ends, we're going to extend the bundle to end at the maximum of, oh my gosh, of end time and the current bundle's end time. Whatever, it's fine. Just leave it like that. Otherwise, else start new bundle. Right? Because if I don't overlap with the previous thing, right? If I don't overlap with the end of the bundle, then I'm not a part of that bundle and I'm going to start a new bundle, right? And that's what exactly what happened here, right? As soon as this had no overlap with the previous bundle, I started a new bundle, okay? So then how do we determine the total number of placements? Well, let's assume we found all the bundles, right? So there were n bundles. Why did I make that so ugly? So assume we found all the bundles and there was n bundles. So this is just a statistics problem, right? So there's n bundles, right? Each bundle can independently decide if it wants to be in group A or group B. So this can be in 2 places, this can be in 2 places, this can be in 2 places for all the bundles. So each one can be in 2 places. There's n bundles, so that is 2 to the n total placements. So what we have to do is just find the total number of bundles and then take 2 to the power of the total number of bundles and return that. That's as best as I can explain it. Okay, so the first thing we'll do is we'll sort ranges in place. Okay, and then we're just going to keep track of the bundle. So first we'll create a solution res, and then a bundle. We'll set it to 1 because there's at least one bundle, which is the system itself, right? Because they can both be empty. That's one orientation. Okay. So how are we going to do this? So I'm going to set this to negative infinity, and I'll explain why in a second. So we're going to look at each start time and end time in ranges. And then we're going to ask this question, right? If the end time is less than the bundle's end time, which is bundle -1, right? So if the end time, if we end before the bundle ends, then we're a part of that bundle. No, wait. Sorry, I'm an idiot, dude. If we start before the bundle ends, right? Which is a generalization of saying, if we have this bundle and it ends at this time, if I start before that bundle ends, then I'm a part of the bundle and the bundle gets extended. Right? So if I start before that bundle ends, then I'm a part of that bundle. So then we would say, okay, now the bundle ends when? Bundles. Bundle ends what we thought it was, or the end time. So why is this the idea here? Why is it not just the end time of the current object? Well, the thing is you could have a bundle like this, right? Imagine this was the bundle length. Typically, we've been dealing with examples like this, so the bundle gets extended to this point. But technically, you could have something added that looks like this. So there is overlap, but the thing that starts later ends earlier, right? So you have a really long meeting down here and a shorter meeting up here, but they have direct overlap. And the newest element, although it starts later, it also ends earlier. So the boundaries of the bundle are still the same. So you just take the max of this end time of the event you're looking at and the max of where the bundle is ending currently. Okay, otherwise, if I don't start before or during, right, because they could overlap at the edge. If I don't start before or during the previous bundle's ending, I've just created a new bundle. So now then that means that we've created an additional bundle. So we'll times equal 2, right? Because we're going to do 2 to the n. So if I just keep multiplying 2 every time I encounter a new bundle, that'll have the same effect. Don't forget, though, almost forgot. We're going to mod it. (10 to the 9 plus 7). All right. And then we're going to recreate our new bundle now. So now we'll say a bundle. If they didn't intersect, then our new bundle is just the current event we're looking at, right? So that's just start to end. All right. And at the end, we just return res. There you go. And I guess we could technically, just to make people angry, right? Because this is the same thing as doing 2 to the n, because I'm just doing I'm just multiplying the res by 2 n times, right? And that's what an exponent is. 2 to the n is just applying the operation of multiplying by 2 n times. So I'm doing essentially the same thing, just in place for space complexity. Okay. And I'm going to make this even shorter because I really hate you guys. All right. And look at that. 5-line solution. All right. Awesome. So what is the space and time complexity of this problem? Well, let's say that n is the length of ranges. Okay. In terms of time, well, the kind of overshadowing term here is sorting, right? Because sorting is going to take big O of n log n time. And then we have to look at all items within ranges, right? All n items. But for all n items, we just do 2 constant operations, right? We make a comparison and then we set some value, right? Depending on that comparison, we set 2 separate values, but we just do constant things. So we look at all n elements and do n constant things. So that's n log n plus n, but n log n is going to, over time, right? In the worst case, n log n, not in the worst case, n log n is going to overshadow n for large enough n. So we just say that n log n is sufficient here to explain this time complexity. And then for space, well, we have to sort ranges, but the way that we're doing this, we could use like in-place heap sort to sort ranges in place, so that it uses no additional memory, right? It doesn't scale with n. And then we look at all the ranges, but we only keep, we just keep setting bundle, right? This one bundle array, and then when we encounter a new bundle, we discard the old bundle array and look at the new bundle array, because we're only looking for the total number of bundles. We don't need to actually know like the boundaries of each bundle. We just need to know the total number of bundles that exist so that we can calculate the total number of placements, right? So for that, that would be O of 1, right? Because I insort ranges. So if ranges is 10 items or ranges is 1,000,000 items, in place sort will operate independently in terms of the amount of space that it uses. And then regardless if I have 10 items or 1,000,000,000 items, right, I'm always just looking at one bundle. So there you go, everybody. I hope you have a beautiful day.